Okay, guys, welcome back. Sorry for the delay. Had a technical problem here. In fact, I may need to stop. I got the carpet cleaners coming, so I may need to stop for a few minutes and let them in and so forth. So we'll proceed. I'm not quite sure what time they come in. They say anywhere between noon and 8. So doesn't help me out very much. Anyway, a couple of things. Obviously, we got spring break next week. Yes, we do have a live on Friday. I also, you may have seen your grade kind of drop pretty quick. Well, don't get too razzled about it. I explained this last time about the nomenclature exam. It is a reminder, it is worth 10% of your grade. I sent an email to that effect of what I did. If you, as per the departmental policy, you need to have at least an 80% or greater to pass that particular assignment. Anything less than that gets dropped to a 0. Okay, you have unlimited number. And yes, I know it's not due to the end of the semester, but I put that number in there now because it gives you a better feel for your overall grade. What's happened in the past is I would wait until it was due last week of the semester. And if you were on the border, it would drop your grade drastically, as you probably saw right now. And it freaked students out. They only had a few days left over to attempt to pass that. So to prevent that added stress, I do it early in the semester around midterm. So you have the rest of the semester to complete it and get that 80%. Okay. Now, obviously, as we proceed with the assignments, your grade will go up, hopefully, right? It goes up and gives you a better idea of your exam, but I mean, your overall grade. But right now, you can see that that 10% can have an effect on the grade. And if we were to stop the semester right now, unfortunately, that would be a grade. Obviously, there's a lot more assignments coming and so forth. So you're not sitting there at whatever grade you have. Now, if you're on the border, it may have an effect, may not. Okay. Let me restate that. If you're not on the border, that 10% may not affect you. And students in the past have ignored it. And okay, that's up to you. This is your class. This is your course. But I just want to demonstrate what that grade does. Now, what happens too is as you take that quiz, I go in there and I look at your questions and your answers because Canvas doesn't always grade them properly. So you'll see that I'll put the correct answer in the comments and give you credit for the ones that are correct. And then if you made that whatever greater than 80%, it stays. If you did not, it gets dropped to 0. Okay. Any questions about that? All right. Excuse me. I got 2 Kimberlys. I'm just looking at my list here. All right, that's fine. All right, let us continue then. I believe that's all I had to say. Double check. Yeah. All right, so let's go to where we left off. In fact, we are doing the nomenclature start at number 7. Okay. According to my records, we stopped on slide number 7. Okay. Now, we just finished talking about the anions and the cations, and specifically looking at the atoms themselves and what charge they would have. Remember, the metals are lose electrons and become positive or cations, and nonmetals gain electrons and become negative. The magnitude of their charge is plus or negative is dependent on what group they're in. Okay, so we went through groups 1 through 3. Okay, that have a +1, +2, +3, respectively. These are the metals. Okay, we talked about the term oxidation state. I think I did explain why we use the term oxidation state. Oxidation state because it encompasses the overall state, be it a covalent compound or be it an ionic compound. Okay. It's still, we're talking about a charge, but the term oxidation state is preferred. Now, we did mention that there are 16 metal ions that you have, 100% of the time what their charges are. And to refresh your memory on that, let's go to my periodic table, and hopefully you marked your periodic table, but these in circles, these atoms encircled. The group 1, everybody from lithium on down have a +1. Okay, they have 1 valence electron. Their metals are going to lose 1 electron, so they end up with a +1 charge. Group 2, okay, starting beryllium all the way down, those have 2 valence electrons. Okay, when they become cations, they end up with a +2 charge. So right there are 12 total elements that have a constant exact oxidation state. Okay, 4 others are given to you here. Aluminum, number 13, has a +3 charge 100% of the time. And then going into the the transition metals, the B elements here, we have zinc, which always has a +2. Silver always has a +1, and CD or cadmium always has a +2. So those 16 metals, 100% of the time of their oxidation state. That means that all other metals, all the other ones have a variable oxidation state. And I use the example up here for example, copper can exist either as a +2 state or can exist as a +1 state. And we have to differentiate between those two. Okay. And the way we do that is we utilize Roman numerals. So let's go back to the slide here. And so, for example, copper 2 +2 down here in the bottom would be written as copper Roman numeral 2 in parentheses. That Roman numeral, I can't overemphasize, has nothing to do with the Roman numeral of the group number. Totally unrelated, okay? And so if you see written out as iron Roman numeral 3, all that is telling you is that you're using the iron in the +3 oxidation state. Okay. And the same is true for the other example right there with lead. Lead Roman numeral 4 is telling you you are working with oxidation state lead +4. Okay. All right. So with those 16, they have a constant oxidation state. Therefore, we use no Roman numerals for those 16 when we need to name them. Okay. No Roman numerals. That means all the other ones will require an Roman numerals because their variable oxidation state can vary from a +1 all the way to a +9. Okay, depends on the metal. Okay, so let's continue. The anions, we talked about these also. These are nonmetals that gain electrons. And so everybody in group 5 will have a -3 charge. Everybody in group 6A will have a -2, and 7A will have a -1. All right, so what I I don't have my mark, but you could, if you wanted, deal with the markings here. So -3 in this group, -2, and -1, okay? And that's because that's how many electrons they need to be isoelectronic with a noble gas in front of it. Remember, the goal here is when metals lose electrons and nonmetals gain electrons is to have the valence electrons of 8 around it. And losing electrons like the metals do means that the next energy level that's in has 8 electrons around it. Gaining electrons means that it starts to, whatever valence shell it has, is going to pick up either 3 or 2 or 1 electron to fill that outermost shell to give you that magical 8 number. Okay. All right. So and of course, the noble gases, they don't have an oxidation number. Why? Because they have their octet is fulfilled. Helium has its duet, so it's not going to have an oxidation number. All right, so we're going to combine ionic compounds with respect to metals and nonmetals. So we're going to start learning the formulas and the names for ionic compounds, okay? Now, the thing to remember about this is when we start putting these compounds together, that the sum of the oxidation states, the sum of their charges must equal 0. Okay. And another way to write this is to put it this way, that the number of cations plus the number of anions is equal to the overall charge of the compound, okay? Now, 99% of the time, that's going to be equal to 0. This equation I just wrote for you is kind of encompasses all types of scenarios that you may have. Now, like I said, 99% of the time it equals to 0, but you can have a time when it's not equal to 0. For example, the polyatomic ions that we work with, where we have SO4, for example, sulfate, okay? We may need to know the oxidation state of sulfur, okay? And we can do that. We can calculate it because we're going to always know the oxidation state of one or the other, either the negative or the positive. In this scenario, the overall charge for the sulfate is a -2. Okay. And so that's why this equation I just wrote kind of encompasses all of the scenarios. But most of the time, they're going to be equal to 0. We're going to run some examples of both. Okay. All right, let's do this. Now, polyatomic ions, remember that it's on the periodic table. So you become familiar with it. Okay. These polyatomic ions, these are units. Okay, we don't separate them. We keep them together. They have their own name, very specific name. So if we look at one, for example, let's take a look at this one here, the nitrate. It is NO3 -1. Polyatomic ions are made up of covalent compounds that have a negative charge, but they're ions, okay? It has the name of nitrate. Okay, notice the suffix ATE, nitrate. Totally different from if we start the common factor here for nitrogen. We got N for nitrogen. Okay, when nitrogen becomes an anion, it gains 3 electrons, and remember what we name this? Nitride. Okay. Now, when we start getting nitrogen bonded to oxygens, and we're going to have a PowerPoint on this too. We got this one's called nitrate. Okay, nitrate. And then you can have the NO2 negative that is called nitrite. ITE. Notice the suffix. We start with nitrogen, then becomes the anion. The IDE tells us it's simply the atom with its respective charge, oxidation number, that's just nitrogen, or the IDE, ide. Then when you hear the ATE, that tells you we got nitrogen, but it's bonded to oxygen. And in this case, it's bonded to 3 oxygens. And when there's one less, and that this is the parent polyoxide, polyoxygen ions. When it is ATE, this is 3 oxygens. If we remove 1 oxygen, then we have the ITE, the ite. Okay. Now we're even going to have more. We can continue to remove 2 more oxygens for nitrogen. For the oxygen, we can subtract all the way back till we get to nitrite itself. This is a whole nomenclature PowerPoint slide that we're going to do after the fact. Okay, so but the takeaway here is this: for these polyatomic ions, if we need more than 1, then we got to put a parentheses around it. So for example, if I have X, whatever X is, the metal-wise, and I need 3 of the nitrates, then I would put nitrate polyatomic ion in parentheses with a subscript 3, okay, or 2, or whatever number I need, okay? And this is true for all of these polyatomic ions. This, by the way, is not an exhaustive list of all the ions that exist. It's the most common ones that we're going to utilize in our class. Notice a majority of them are all negative anions. We only got 1 positive or cation that we utilize. Okay. Okay. So we keep it together as a group in their own specific name. We don't change the name. Like, let's go back to nitrate. It's nitrogen with 3 oxygens. We don't go back and say nitrogen trioxide or something like that. It's simply called nitrate. Okay. Now, compounds must be neutral when we put them together. So we have to add enough cations, enough anions to equal 0 for 99% of the examples that we do. Okay. All right. So let's combine sodium with nitrogen. Well, to do that, the first thing we need to do is to convert the elements into ions. And that's why we need to know what their oxidation state is in ionic form. We know that sodium is a group 1A, so therefore it would have a +1 charge. Nitrogen is a nonmetal. It will gain 3 electrons, and therefore in ionic form, it will have a -3 charge, okay? So we take the elements, put them into ionic form, okay, with the correct charge, and then we combine them such that we have enough of each to cancel everybody out to end up 0. You can see here that we need 3 positives to cancel out the -3 of the nitrite. So that 3 in front of sodium ion becomes a subscript. So the formula for this compound would be Na subscript 3N, okay? Its name would be sodium nitride, okay? So from here, we went from a formula to the name, but be prepared to go from the name to the formula, okay? And in either way, whichever direction we're going, the ultimate goal first to go one way or the other is to first put everybody in ionic form so you can put everybody together with the correct number so that the overall charge will be equal to 0. All right. So there's a formula Na3N. All right, well, let's work through some other ones. Again, we have sodium and we have sulfur. All right, sodium we just talked about always has a +1, okay? And sulfur is a group 6 nonmetal. So it would end up with a -2 charge, okay? Now that means we got to put these two together with 2 cations for one of the anion of sulfide. So its formula becomes Na2S. Okay, let's try magnesium and oxygen. Well, magnesium is a group 2 metal, so that has a +2, and then oxygen, like sulfur, all right, we'll come back to the names here in a bit, has a -2. Okay, so in this scenario, I can put them together, the ions, as a 1-to-1 relationship ratio, because one has a +2, the other one has a -2, they cancel each other out. Okay. Excuse me 1 minute, I gotta put the dog away. My apologies, the disadvantages of teaching from home. Anyway, so there is a formula for magnesium and oxygen. To give you the formula MgO. The next example is potassium, which, as the case of sodium, is a group 1 metal, so it has a +1 oxidation state. And phosphorus is a group 5 anion, okay, meaning that it becomes a -3 anion. All right, so then we need 3 potassium cations to counter the -3 of the phosphide anion. So its formula becomes K3P. All right, this one's a little more challenging. We have calcium, which has a +3 charge, and then nitrogen, which ends up with a negative. Excuse me. Anybody see what I did wrong here? With respect to calcium and nitrite? Nobody see that? What's wrong with what I wrote here? Or is there anything wrong with it?
The calcium's a +2, right?
You got it. Yeah, exactly. Okay. So it's a +2. Thank you. So I got the +2 and I got the -3. Okay. The previous examples that we're doing is fairly straightforward. I got, it's either a 1-to-1 relationship, or I could add 2-to-1 or 3-to-1 or whatever the case may be. Here's not so straightforward. I got a +2 and a -3 that I need to combine. Well, when you come across this scenario, what you have to do is find a common number and look at the number 2 and 3. What is a common number we have between those two numbers? What can you think of? It's very analogous to adding, let's say, +3 plus a 1/3 plus 1/5. What do we do in that scenario mathematically? When we're going to add a third and a fifth, what do? We look for a common number, right? Convert each fraction to that common number. Okay, Ashley, you had your hands up.
The +2 on the calcium, that came from the periodic table, right?
That is correct.
Okay. Just making sure.
Sure, it is a group 2 metal, so it will have a +2 charge. Okay, now how can I combine these two together now? The +2 and the 3, the -3. What common number do they have?
6.
You got it. Okay, just like up in here, common number could be 15, so we convert each one. So here we got a 6. That's our common number between the two. So that means that I need 3 calcium +2 charges to give me a total of +6, right? And how many nitrides do I need? I would need 2 to give me a total of a -6. All right, so I got +6 from 3 calciums and -6 from 2 nitrides. So these numbers here become the prefixes. So it's calcium prefix subscript 3 and subscript 2. Okay, and that is the formula for the calcium and the nitride coming together. All right. Now we have aluminum. Okay, so we have aluminum. We go find aluminum. Aluminum is a group 3A. It has 3 valence electrons. It would have a +3 charge. The chlorides is in group 7. It's a nonmetal. They're going to have a -1 charge. Okay, that means I'm going to need 3 chlorides for every aluminum +3. So my form, yes.
I'm confused how it turned to a positive, like a calcium 3 and nitrate 2, but we got 6 out of that. How did that turn to a 3 and a 2 positive?
Okay, we'll go back to that one real quick. Let me clear that up. All right, let's look at calcium. What is the oxidation state of calcium? Remember, it's a +2. Everybody know how we got that?
Yes.
Yes, everybody got that. It's a metal. It's in group 2A. It's going to lose those 2 valence electrons. Then we look at nitrogen. Nitrogen is in group 5A. So it's going to pick up 3 electrons. Okay. Now, I can't put these together 1-to-1, right? Because one of them has a +2 and the other one has a -3. See, the goal here is to put them together so that I have enough of cations and enough anions. So when we put them together, it's going to be equal to 0. If I put these together 1-to-1, I'm going to have an excess of a -1. Can everybody see that? If I put a +2 and a -3 together, I'm going to end up with a -3 net. So it didn't cancel, a -1 net. Follow? If I just did this, I have a -1 left over. That won't work. Okay, so when I have two dissimilar numbers, I need to have enough of the cations and enough of the anions so they equal 0. So if I have 3 calcium positives, okay, does everybody see how I have a total overall of a +6?
Yes.
Okay, and if I have 2 nitrides, doesn't that overall give me a -6 total?
Yes.
Yes. And so now I have enough cations to positive sixes to cancel out the -6 to give me an overall 0. Okay. So that number that I put in front of the nitride and the calcium becomes a subscript. Hence the formula means right there, I need 3 calciums and 2 nitrides. And that is the formula for calcium nitrate.
Okay, I
Does
see
it-
that now. Thank you.
You see that?
Yeah.
So anytime you have a dissimilar number, and here this example is a +2 and a -3, okay? But you could have, reverse it, you could have a +3 and a -2. Same scenario. Our common number would be a 6 in both cases. Or you could have a highly unlikely, but if I had a +2 and a -5, okay, what would be my common number in that scenario? A +2 and a -5.
10.
But exactly, that's the common number. So you find a common number when the two charges are dissimilar. Okay, just like we would add two fractions. If I needed to add 1/3 plus 1/4, what would be our common number here? Wouldn't that be a 12? So I would convert everything to 12s, right? Everybody agree on that? For the math part?
Yes.
Okay, and that's all you're doing. When you have two dissimilar numbers, oxidation states, you find a common number for both of them. All right, another little tip. If you think about this, let me write it a little bit bigger. We came up with this formula. Remember that it's a little guide, a little tool will help you out a little bit when you have these here. Now, remember we started off with a calcium +2 and a nitride -3. Well, think about it. The subscript of the anion of nitrogen is the oxidation state for the cation. See that 2? And the subscript for the anion is the oxidation state, the subscript for the cation is the oxidation state for the anion. You see the scenario there? That it might help you. But if you don't see it, just stick with the common number for right now. I think as you do more of these, you'll see what I just pointed out. Because with that, you can just look at a formula and automatically tell you, okay, calcium has a +2 and nitrogen has a negative, nitride has a -3. Just based on the subscripts of their respective partners. All right. Aluminum had a +3 and the chlorides each had a -1, meaning that I need 3 chlorides for every +3 of the positive cation of aluminum. And then zinc, there, recall what charge, what's the oxidation number for zinc? Anybody know?
+2.
You got it. And the iodide each have a -1. Okay, so here in this example, I need 2 -1s for every 1 +2 of zinc. And so that 2 in front of iodide becomes the subscript for iodide. So its formula will be ZnI subscript 2. Okay, now here's the Roman numerals, okay? What does this Roman numeral represent now? Remember, it has nothing to do with the Roman numerals of the group numbers. What does this Roman numeral mean?
+2.
You got it. That Roman numeral tells you that you are working with +2 ion of copper, okay? And if if it was written like this, in that case, you're working with copper +1. Okay, copper exists in two variable states, either +1 or +2. And to distinguish the two, we use the Roman numeral nomenclature. Oxygen, again, group 6A, and it's a nonmetal. It will pick up 2 electrons, and therefore it has a charge of a -2. So in this scenario, I could put the copper +2 together with 1 copper +2 with 1 oxide to give me the formula of CuO. Okay, if I was working with copper 1 +1 and the oxide, well, I would need 2 copper 1s in an oxide. And its formula will be Cu2 subscript 2O. Okay, that will be using copper 1 oxide. 2 complete compounds, copper 1, copper 2. One of them in solution is a nice blue, beautiful solution color, blue color. And the other one is a green color. Totally different ions, different properties, same element, just a different oxidation state of that element. And then this one here, lead. Pb is lead, but which one are we working with? What is the oxidation state we are given? What does this tell you?
+4.
You got it. So we're working with +4 ion, okay, for lead. And then the oxide, as the previous example, has a +2, okay? So that means how many oxides do we need to counter the +4 of the lead? How many do we need? If each
2.
2, you got it. I need 2 of them. So my formula is PbO subscript 2. Okay. All right. Let me go back. Okay, let's work on the names. Okay, first one, top one was sodium. What about the S? Well, what do we call that? Sodium sulfur? Would that be correct? Remember what happens to the name of the anion when it becomes, and when it goes from the element to the anion, what happens to the name?
It becomes the IDE version.
You got it. So what do you expect its name for sulfur to be now?
Sulfide.
It's sulfide, exactly. Okay. And then we have magnesium. Notice nothing changes to the name for the metal remains the same. Oxygen now becomes what? What do you guys think?
Oxide.
Oxide, exactly. Okay. Then we got potassium. P becomes, what do you think? Went from phosphorus to
Phosphide.
phosphide, exactly. Now you're getting to notice a little trend here, the IDE. That when you see the IDE, then whatever the front name is, that's just simply that atom by itself. Okay, and I'll show you an example here in a minute. And then where we at? Potassium, now we got calcium. And then nitride. Everybody agree on that? Nitride, I'm going to run out of space here. Okay, and then we have aluminum chloride. Okay, and then we have zinc. Whoop. Zinc iodide. Okay, all right. Notice that in these examples, all these metals, we did not use the Roman numerals. Why? Because those metals belong to the 16. Remember that list I went through with the 16, group 1, group 2, coupled with aluminum, zinc, silver, and cadmium? There's 16, call it the sweet 16. They have an exact oxidation number, okay? Therefore, because they have an exact oxidation number, we do not use Roman numerals. It is only when you have a variable oxidation state, like the copper, that we require to use Roman numerals. So this means this for copper, for the number 7, it is copper, write it out, copper, Roman numeral 2, and it's all uppercase, and then oxide. Okay. And then number 8 is lead, Roman numeral 4, oxide. Okay, so the Roman numerals are used for those metals to have a variable oxidation state. And you have to include the Roman numerals, and it's uppercase Roman numerals in parentheses. Okay, because what used to be done is to name this with prefixes of their own. Copper 1, copper 2 were being called cupric and cuprous, and it was very ambiguous. It's trying to keep the us and the ick and everything else straightened up. And so the international organization got together and said, hey, we're going to start naming, they're the ones in charge of naming chemical compounds. It's everybody in the world, chemists, countries are members of this group, and everybody agrees to how to name compounds so there's no ambiguity. Okay, so only the 16 do not require Roman numerals. Any other metal other than the 16 requires Roman numerals to distinguish which oxidation state they're in. Okay. Now, at this scenario, we just use the metal given and the non-metal given. But you know what? You can do mix and match now. We did sodium sulfide, but you know what? You can combine it with sodium oxide, sodium phosphide, sodium nitrite, sodium chloride, sodium iodide, etc. The same is true with magnesium, magnesium sulfide, magnesium phosphide. See how you do the mix and match? You can start building up a database of all these compounds that you are making. Okay. Now let's go back to the I part, and let's just take sulfur, because this is true for nitrogen and it's also true for phosphate. Let's just do sulfur. Okay. Sulfur, the element, its name sulfur. Okay. Sulfur, the anion, -2, is sulfide. Okay. Now, sulfur that has been bonded to oxygen, specifically 4 oxygens with a -2 overall charge, the polyatomic ion, its name is sulfate. Okay. And then if there's one less oxygen, SO3 -2, it is sulfite. Okay, and so we have the prefixes ate, ite. The 8 tells you, yes, all of them, look at the SUL, all of them deal with sulfur, the symbol S. Sulfur is simply the element. The sulf is sulfur, but then the IDE tells you it is the anion. And when it's IDE, it is specifically just that element itself. When we do ATE, ITE, now we start introducing oxygens bonded to that element, in this case, sulfur. So the sulfate, sulfite, okay, those are polyatomic ions, okay, which is sulfur bonded to oxygens. All right, so, and it's so crucial to remember the naming here. So if we go back, let's do very quickly, go back to the periodic table and just look at the anions. You can see here that we have the nitride, the phosphide, the oxide, the sulfide, and we can go up the arsenide, the seleniumide, so forth. Then we got the fluoride, chloride, bromide, and iodide. Okay, those are the prospective anion, be it a -3 charge or -2 or -1. But because it's IDE, it's simply the element in an anion form by itself, the element by itself. We start throwing in the 8. Now we're talking about putting in oxygens or the ite. Okay. So every time we put a metal, non-metal together, okay, we make sure they put them enough anions and cations so they end up with a 0 charge for neutral compounds, neutral ionic compounds. Okay, every one we did here has a neutral charge. However, there are examples where you can have a non-neutral charge. Let's run that example here. Let's work with the sulfate, SO4 -2. Okay. Now, normally sulfur, when it's by itself, will always have a -3 charge, oxidation state. Okay, the sulfide. But when it becomes the sulfate, it is the central atom. And we did this in the Lewis dot structures. Sulfur is a central atom with the 4 oxygens bonded around it. Okay, came up with that Lewis dot structure. Okay, so it no longer has a -2 charge, but we can calculate it. We can calculate it. Why? Because as I gave you the general formula before, I said that the number of cations or the positive charges plus the number of negative charges must equal the overall charge of the molecule. Okay, so let's run it through. Let's find out what is the oxidation state of sulfur in the polyatomic ion sulfate. Okay, well, we don't know what that is. We put sulfur, but we do know what is the oxygen. What is the oxidation state of all the oxygens, be it in ionic form or covalent form? What do we know about the oxide? What is this charge 100% of the time? Oxygen. What is this oxidation state?
-2.
You got it. -2. Now, how many do we have here? We got 4. So we have a total of -8. Everybody see that? We got 4 oxygens, and each one has a -2. The overall charge of this ion is a -2. So here it is, the cation plus the anion equals the overall charge of the molecule, which is -2. So we have a very simple algebraic equation here. We gotta solve for sulfur. So sulfur is equal to 8 minus 2 is equal to +6. Okay, so that means that in this state, as a sulfate polyatomic ion, sulfur exists as a -6 oxidation state. Okay, and that each oxygen here has a -8, and that equals the overall charge of -2 for the molecule. Okay, the point of this exercise is this: we're always going to know the oxidation state either of the anion or the cation and the overall charge. And with that being said, we can calculate one or the other, okay, and determine which one we are using. For example, all right, what if you're given this formula here? Okay, FeO, and you're asked to name it. Okay, well, I know Fe is iron. Okay, I also know that iron is not part of the 16. So that means that I'm going to need to use Roman numerals to describe this particular iron. Okay, so that's why I put parentheses with a question mark, because I don't know what it is. And then the oxygen will always be called oxide. Okay, here's the thing to remember. The counterpart here, the anion, will be always named the IDE, be it ionic compound or be it covalent compound. Okay, you know, CO2, what do we name this? Carbon dioxide, oxide. Okay, and this is a covalent compound. FeO, that oxygen is still called oxide. Okay, remember that. And if it was sulfur, it would still be called sulfide, be it ionic or be it covalent. All right, now we need to figure out what is the charge of the iron. Okay, well, we can see what we're given here, it is a neutral charge. It's a neutral species, so the overall charge is 0. Okay, I don't know what the charge is, oxidation state is for the iron, but what do I know about the oxygens? What is their oxidation state all the time?
+2.
Oh, not the oxygen, it's a nonmetal. For the oxygen, what is the oxidation state for oxygen? All the time. It's a 2, but is it +2 or -2?
Negative.
All the time, 100% of the time, always a negative. Remember, it's a nonmetal, so it's going to gain electrons, okay? And it's going to gain them, be it ionic or covalent. It's going to have a negative charge, and it's always going to have a -2 charge. All right, so my general algebraic equation is iron minus 2 equals 0. What must iron be in order to combine with a -2 to equal 0? Okay, what must be the oxidation state of iron?
+2.
Exactly. So it's a +2, a -2, and that equals 0. So this means that this in parentheses has to be Roman numeral 2. Okay. So it is iron Roman numeral 2 oxide. So here's an example of, I don't know what one of the partners' this oxidation state is, but I do know the oxidation state of the other partner. Okay, because they could be going both ways, be it the negative part or the positive part. In this case, we knew the oxide, but we didn't know the positive part. So we calculated it because we also know from the formula given that it's equal to 0. Okay, so we can calculate what the oxidation state would be for iron. Okay, what about, let's demonstrate that with this formula where we have Fe2O. Okay, and in this scenario, you're being asked, what is the oxidation state of iron? Okay, well, and the overall is neutral. So what do we know? We know there are 2 irons, and the oxygen, again, is -2, and that is equal to 0. Okay, so there's my algebraic equation, 2 irons minus 2 equals 0. I can rearrange this and say, add a +2 on both sides of the equation. I have this, 2 iron is equal to a +2, and divide through by 2, which means that each iron must be a +1. Okay? Now, let's do it this way. Does it make sense that if I have 2 irons, and that's a -2, that each iron must be a +1 if I have 2 of them to cancel out the -2 to equal 0? Okay. Therefore, its name would be iron, Roman numeral 1, oxide. Okay. Very similar to what name-wise to the one we just did. Both of them have the parent name iron oxide. Okay, iron oxide. Where they differ is the Roman numeral. This one had Roman numeral 1 because we're using the iron with the +1 stage, the way I wrote it. And this one has the Roman numeral 2. Roman numeral 2. Okay. Now, though I did use iron 1 in this example, it was just for demonstration purposes, because in reality, there's an iron +2 and there is an iron +3. Okay. I didn't want to introduce that. I kept it simple for right now, just to demonstrate how we can calculate that iron oxidation state under this form right there. All right, let's formulas with polyatomic ions. Okay. All right, so we're given the Mg. Okay. And like we did before, when we're given the elements, now we're just going to be given the element on one side. The other is the polyatomic ion because it's given to you. It's got a -1 charge. Okay. The fact that's the case, what you do is you go to your polyatomic ion table down here. Okay, you see the OH minus right there. Okay, you need to know what its name is. Its name is hydroxide, because you're going to not only write the formula, but you're going to be able to write its name. So the OH negative is called the hydroxide. And you get that from the polyatomic ion table. It's got a -1. All right, so what do we know about magnesium? What is the oxidation state of magnesium?
+2.
It's a +2. And we know that the hydroxide is a -1 because it's given to us, okay? So that means that I need 2 hydroxides for every 1 magnesium. The fact that I need 2 tells me that I need to use parentheses around the OH because we want to keep them together as a group. We don't want to separate them. So we use a parentheses, okay? OH2 here, that tells me I need 2 hydroxides because each one is a -1, okay? It's incorrect to say, okay, since I need 2, what if I make O2H2? That is not the correct way. I have no idea what that is. I've seen that before. They're figuring that I need 2 of them. I just put a subscript under the oxygen and the hydrogen when that's incorrect. We put a parentheses and then use the subscript to tell you how many of those polyatomic ions you need. So its formula is MgOH parentheses 2, okay? All right, here we have potassium and note the PO4, -2, okay? Direct you to your polyatomic ion table and guess what? Its name is phosphate, okay? The potassium, or excuse me, yeah, potassium has a +1 charge. That means we need 3 of them because the phosphate has a total -3. So I need 3 potassiums for every PO4. Now this polyatomic ion, whenever you just need 1, you just leave it as 1. You don't need a parenthesis, okay? Nor do you need a parenthesis around the potassium. You just make that a subscript 3. All right, here we have sulfate, SO4 -2, and then Ag. Do you guys remember what is the oxidation state of silver? It's 1 to the 16. Okay, always has a +1. The sulfate has a -2, so that means I need 2 silvers for every sulfate. So its formula is Ag subscript 2 SO4. All right, here we have calcium, and then the NO3- is called the nitrate. We'll come back and name all these here in a bit. Calcium has a +2. Okay, and that means we're going to need 2 of the nitrates, the NO3. So we're going to use parentheses to wrap it around the NO3 and make it a subscript 2 to give us that formula. Okay. Next one, here we're dealing with the carbonate, CO3 -2. And the copper, what is the oxidation state of the copper we're working with here? What does that tell you?
It
What's
has
the,
a +2
it's
charge.
there's a +2 charge, exactly. So I got a +2 on the copper and a -2 on the carbonate. And so I can put those together as a 1-to-1. So CuCO3. Okay. And then the point, let's get the name of these. Okay. We had magnesium. What was the name of the OH in parentheses?
Hydroxide.
Hydroxide. Okay. And then we got potassium. How about the name for the PO4? Check your polyatomic ion table.
Phosphate.
Phosphate. Okay, and then we got silver, SO4, that would have been sulfate. Okay, then we got calcium, the NO3 in parentheses is called nitrate. And then Cu means copper, and note that because it's variable metal, we have to use a Roman numeral. And then carbonate. Okay, so we got magnesium hydroxide, potassium phosphate, silver sulfate, calcium nitrate. Okay, note that for these examples, no Roman numerals. Okay, because we didn't say magnesium Roman numeral 2 hydroxide. We didn't say that. Because those metals, potassium, magnesium, silver, and calcium, the ones we just used, those are the 16 that have an exact oxidation state and therefore do not require Roman numerals. Copper, on the other hand, has 2 variable oxidation states, either copper 1 or copper 2. And so we have to be specific as to which one we're working with. And we're working here with copper 2, which is the +2 ion. Okay. Now, again, you can mix and match, because you can do magnesium phosphate, magnesium sulfate, magnesium nitrate, and magnesium carbonate. You can do silver hydroxide, silver phosphate, silver nitrate, silver carbonate. Same with calcium, calcium hydroxide, calcium phosphate. So again, you start mixing and matching the metals and the nonmetals, and you can do a series of compounds. Start building up your database. Okay, so you're not limited to just specifically what you're given here. You can mix and match. Okay, and of course, if you need to write the formula, mix and match properly so you have enough cations and enough anions so they cancel each other out. Because all of these here, notice the final formula that we put together is neutral. There's no charge on the magnesium hydroxide, potassium phosphate. The charges come into play beforehand when we put them together to make the compound, to write the formula. Okay. So we up to this point, we've been using writing the formulas. Now we're going to talk about given the names, okay? Given the formula, write the name. So you can see here we got Na and Cl. Well, we got Na, which is sodium, and it's combined with the Cl, which is chlorine, but it is the ion chlorine, so it is chloride. So the name is sodium chloride. Again, notice we didn't use Roman numerals. It is not sodium Roman numeral 1 chloride. It's simply sodium chloride. Okay. How about this one? We got KBr. What do you think the name is here? K would be potassium. What about Br? Would it be bromine, potassium bromine? Would I be correct to say potassium 1 bromine? Okay. Is that name correct? If you could read my writing, my pen here, resolution, not the rest. I wrote potassium, Roman numeral 1, bromine.
No.
No. what is wrong with that name I just wrote? There's a couple of things wrong with that name.
It needs to be bromide.
Okay, that'd be wrong because it's bromide. Okay, because it's an ionic form. Okay, if this was bromine, then it would be elemental form. Okay, what else is wrong with the name as I wrote?
I don't think there needs to be a Roman numeral.
Exactly, because potassium is part of the 16, those elements I went to, and because of that, no Roman numerals for them. They have an exact oxidation state. Okay, so the correct name would be potassium bromide. Okay, that's good. Be aware because sometimes you can have questions where they're throwing a name out like that and said, "Is this the name for this compound?" And you're being asked to analyze it, and no, this is wrong. This is wrong. Okay. All right. So its name is potassium bromide. All right. Here we have magnesium and oxygen, which would be, who wants to take that one?
Magnesium oxide.
Magnesium oxide. Here you go. You got it. All right. Then we have calcium. Now, a lot of people will see that F2 and think, oh, I'm working with fluorine. Okay. And write down calcium, fluorine. Okay, well, as you hopefully know by now, with the I and E, and they write fluorine because they see a subscript too, and they're thinking this is what you're working with, okay? But the thing to remember is right in front of the F2 is a metal. The fact that there's a metal first followed by Fe2 tells you that no, it is not fluorine, it is fluoride. If it was written all by itself like that, yes, that would simply be fluorine. And if it were written with a space in between them, well, we got two species here. One, we got calcium, and second, we got fluorine, two different species. Okay, but the fact is they're put together, telling you it's a compound, specifically an ionic compound. Calcium fluoride. And then we got this one. How about number 4? Who wants that one? What do you think? Li would be what?
Is it lithium?
Lithium, that's correct. What about the,
Lithium sulfide?
you got it, lithium sulfide. Okay. What if I wrote dilithium sulfide? Is there anything wrong with that name?
Does that mean it's a diatomic element, which it's not?
Yeah, but the di means there's two lithiums, right? Not necessarily diatomic, just two of them. Or if I would have written calcium difluoride, what is wrong with both those names? If I write calcium difluoride or dilithium sulfide, you
It doesn't
remember
need a prefix.
exactly. Remember, ionic compounds, no prefixes. No prefixes. Okay, so that would be incorrect, and that would be incorrect. And you find it in labels sometimes. They use prefixes for I don't know, for whatever reason. As I read labels, I see the prefixes. They may have been used a long time ago, but for ionic compounds, there is no prefixes at all. Okay. Okay, good. No prefixes. All right, then we have Ag, which is silver, and then Cl, which is chloride. So we got silver chloride. And then again, the re-emphasis on no prefixes for ionic compounds, which are going to be different with respect to covalent compounds. In covalent compounds, we do utilize prefixes, okay? Remember to distinguish the two. Ionic compounds is a combination of metal and nonmetal, and covalent compounds is a combination of nonmetals. All right, here they're asking you to, well, here we're using it, we're still going with the name, but we're working with polyatomic ions, which can be challenging to determine whether you have a polyatomic ion. But here's one way to look at this, to help you out, to realize that, hey, I'm working with a polyatomic ion. One, obviously we've got K, which would be potassium, okay? And then we see phosphorus, which obviously you got a metal, non-metal. We're thinking phosphide, okay, initially. But then we look and we see right immediately afterwards, we have an oxygen. The fact that we have the phosphorus bonded immediately to an oxygen, there's an oxygen coming, should tell you that no, we're not dealing with the phosphide, but we're dealing with either the ate or the ite. And so you go to the polyatomic ion table and you will see that the PO4 -2 is the phosphate, okay? So we're dealing with the polyatomic ion, and therefore its name would be potassium phosphate. Okay. The fact that you see a parentheses right there should direct you to the polyatomic ion table. The parentheses indicates polyatomic ion within the parentheses. So we have the OH, which sends you to the table, and you look for the OH polyatomic ion, and you'll see that is called the hydroxide, okay? This is calcium hydroxide. Here, like analogous to what we did with the first one, we have zinc first, and then we see sulfur. And on the surface, we might think, okay, sulfide, but then immediately following that, we have the oxygen again. So then that tells you I'm either dealing with the ate or the ite. And you go to the table, you see the SO4 is the ate. Now, analogous, if you think about it, if you were to see this, zinc S. Well, in this case, is zinc, both of them are called zinc initially, because they both had the metal zinc. And then the top one, because I said there was down the bottom one for sulfur all by itself, that is sulfide, because there's no oxygen immediately following that. Unlike the top one here where we got oxygen, so I go find that and it's the sulfate. Okay, so we got zinc sulfate on top and then zinc sulfide in the bottom. Okay, here's that IDE again, that IDE telling you that it's just simply that sulfur all by itself. All right, when there is a variable charge, this is where you actually got to sit there and calculate and determine what the charge is. All right, so let's run through this example. We have CuCl2, okay? Now, the overall charge is equal to 0. It's a neutral species. We don't know what the charge is on Cu copper. It's a variable. We don't know which one we're working with, so we have to calculate. Okay, so I set up my little algebraic equation. It's Cu. Now, what do I know about the Cl, the chlorides? What does each chloride have? Its oxidation number. You can tell me what the oxidation number is for every chloride.
-1.
-1. And how many do we have? We have 2 here, right? So we have a total of a -2 charge. So we got copper -2 equals 0. What must be the charge, the oxidation state of the copper we're using in this formula? What number -2 equals 0?
2
Exactly, specifically +2.
+2. Yeah.
Yes, so specifically +2. So that means under this formula, we are dealing with copper, Roman numeral 2, chloride. Okay. Unlike this one, CuCl. Similar scenario to calculate that. Equals 0. We only got 1 chloride, -1. In this case, this must be copper +1. So we got copper, Roman numeral 1, chloride. Okay, for this scenario right here. For this scenario, it's copper 2 chloride. And we had to determine what it was by going through that exercise there with the algebra. Because we know overall 0, we know we're always going to know the charge of either the anion or the cation. In this scenario, we knew the charge of the anion, okay? And so that allows us to calculate what the charge was for the cation or the metal. All right, let's try this one here. We have lead, which we don't know what is charged, but what do we know about the oxide? What is each oxide? What is this oxidation number? All the time, 100% of the time. Who can tell me that? For the oxygen, when it becomes its oxidation number, it gains 2 electrons. What's its new charge now? Its oxidation number.
Is it -2?
You got it. Okay, all the time. Why? Because oxygen is in group 6A. Okay, that means it needs 2 electrons for that octet. So it always will have a -2 all the time. And we have 2 of them. So what is our overall negative charge? If each one is a -2, what must be the overall charge if we got 2 of them? Wouldn't that be -4?
Yeah.
Yep. And it's a neutral species here. We got no charge, no superscript charge, so it's equal to 0. So what must lead be if it's working with a total -4, if its counter is a -4 total? What must lead be?
+4.
Exactly. So lead has to be a +4, which means that we're using Roman numeral IV for +4. Okay, so its name would be lead, Roman numeral 4, oxide. Okay, how about this one? It's nickel. Okay, we know the parent name is nickel. We don't know the charge. And then we're dealing with bromide. So that is the base name. What we need to figure out is what goes into parentheses. And we use parentheses, why? Because nickel is not part of the 16. Okay. All right, so let's figure that out. What do we know about the bromides? What is each bromide oxidation state for each bromide?
-1.
-1. And how many do we have? 3 of them, right? That means that nickel minus 3 must equal 0. Okay, so what must nickel be its oxidation state if it has a -3 to counter?
+3.
You got it. So this means that that Roman numeral is Roman numeral 3. So its name would be nickel, Roman numeral 3, bromide. Okay, don't mistake Mn. A lot of people mistake Mg and Mn. Two different. This is magnesium, this is manganese. Okay. All right. So here we go. We see sulfur and maybe automatically think sulfide, but then we got oxygen next to it. So SO4. So that sends me to the polyatomic ion table. And what is the charge of SO4? It's a -2. Okay. So Mn minus 2, because there's only one sulfate, is equal to 0. What must be the charge for Mn?
+2.
You got it. It's got to be a +2. And then the SO4 is the sulfate. So we have here manganese, Roman numeral 2, sulfate. Okay, and now here we got copper again. Who can tell me which copper we're working with here? Because we have the nitrogen, but then followed by the oxygen tells me polyatomic ion, NO3, and sends me to the polyatomic ion table. NO3 has a -1, the nitrate. So what must copper be here? What is its oxidation state with this formula?
Is it +1?
You got it, +1, because the nitrate here is a -1. And Cu -1 equals 0. That means that it's got to be +1. So we got copper, Roman numeral 1, nitrate. All right, one last one. We have CO, which is cobalt. And then we got nitrogen. Notice there's no oxygen following nitrogen. So that's indication I'm just dealing with the element itself. That's got to be nitride. Okay. And what do we know about the oxidation state of nitride? What's the oxidation state of nitride?
-3.
You got it. So we got CO -3 equals 0. Okay. So what must be cobalt's oxidation state?
3.
Yeah, +3. You're going to be specific. It's got to be a +3 because the nitride is a -3. Okay. And +3, -3 equals 0. So the cobalt we are working with here in this example would be cobalt Roman numeral 3 nitride. Oh, okay, let me clear this up. Okay, now we have iron. Okay, and then Roman numeral something. And then we got a parentheses, which tells you, okay, I'm dealing with polyatomic ion. I go to the table and that becomes, we look that up and that is the carbonate polyatomic ion. Furthermore, if we look at the table, each carbonate has a -2, okay? All right, So let's write our general formula. We have overall 0. We have 2 irons. 2 irons, okay? Each carbonate is a -2, but how many carbonates do we have here total?
3.
3. And each one is a -2, so we have a total of -6. Okay, so 2 irons minus 6 equals 0. Can you tell me what the oxidation state for this iron would be, given that algebraic equation there in a sulfur iron? What number?
Would it
I-
be 3?
Yeah.
Positive 3?
You got it. You know what? I was going to just say, what number times 2 minus 6 equals 0? It's a positive 3. Okay. Or alternatively, I can solve for that. It gives me +6. Okay. And then I can divide through by 2. So each iron is a +3. Okay. That is correct. So its name would be iron, parentheses, Roman numeral 3, carbonate. Now, that's working it the long way. The other way, I hope maybe you recognize that. Notice this. The subscript of the negative of the anion is the charge of the cation. And the subscript of the cation is the charge on the anion. Wasn't each carbonate a -2? And wasn't each iron here a +3? So we can, by just looking at the formula, very quickly determine what the oxidation state is. Now, if you don't recognize that right here, don't worry about it. Do it long ways until you're more comfortable with it, and you can just at a glance look at the charge, okay? By looking at the subscripts of their respective partner. All right, so in this scenario, you're either going to be given the name or the formula. All right, so let's work it through here. Okay, SR is strontium, okay? And then we got the hydroxide. So we're being asked to write the formula, okay? What will be the charge of SR? Anybody have any idea? It's underneath calcium. It's a group 2 metal. What do you think? What is the oxidation state of the ion of SR?
+2.
+2, you got it. Okay, it's element number 38, in case you didn't find it. It's right underneath calcium, which means it's a group 2 metal, which means that it will lose 2 electrons, which tells you it's a +2. The hydroxides each are -1, so that means I'm going to need 2 of them to counter the +2 of the strontium. All right, so I'm going to need parentheses here to write the formula. Oh, I've got it all written up. Sorry about that. So it is SR parentheses Roman numeral 2. So strontium hydroxide. Okay. The gold AuCl2, we need to determine what the Roman numeral is, I should say. And we know that each chloride has a -1, and there's 3 of them. So that means that gold here must be a +3, okay, to counter the total -3 of the chlorides. So hence we use Roman numeral 3. Zinc has a +2, and the oxides have a -2. I can simply put them together 1 to 1 to give us this formula, ZnO, otherwise known as zinc oxide. Okay. The barium has a +2 charge. It's a group 2 metal. And here's the phosphate with a -2. So again, in this scenario, we use a common number, which is 6. So we're going to need 3 bariums and 2 of the phosphates. So we have Ba subscript 3, parentheses PO4, and parentheses 2, or otherwise known as barium phosphate. Lithium is a +1. It's a group 1 metal. Initially, you might think SO3 to be the sulfate, but if you go look that up on the polyatomic ion table, you see it to be the sulfite. Is 1 less oxygen than the 8. All right. So then that becomes, I need 2 lithiums for every sulfite. So we got lithium subscript 2, SO3. And then aluminum has a +3. And the sulfide has a -2. Again, common number, in this case, again, also 6, meaning I need 2 aluminums and 3 sulfites. So our formula becomes Al subscript 2, S subscript 3, or aluminum sulfide. And here we're being asked to just name it. Well, we know the base name is copper and nitrate. Okay, we know it's nitrate because it got parentheses here, sends me to the polyatomic ion table. And I see that the NO3 is called the nitrate. Now the question is which copper we're working with. Well, each nitrate has a -1, and there's 2 of them. That means we got a total of -2 equals 0. And so it's copper minus 2 equals 0. So copper must be a +2. So we're using Roman numeral 2. So copper 2 nitrate. All right. And again, you can mix and match here. You got strontium chloride, strontium oxide, strontium phosphate, strontium sulfite, strontium sulfide, strontium nitrate. See how you mix and match, and do the same with gold. Gold hydroxide, gold oxide, gold phosphate, gold sulfite, gold sulfite, sulfite and sulfate. All right. Okay. Okay. Here, you're given the formula. Okay, you're given a name, excuse me, and you're asked to write the formula. Okay, when you're given a name, what you want to do is you want to first put everything in ionic form. By doing that, that assures you that you have the right number of cations and anions put together to write the correct formula. So let's break it down. Okay, so we have sodium, which we know is a +1. Okay, and then you have nitrate. Okay, nitrate sends you to the polyatomic ion table, and that is the formula NO2, not to be confused with nitrate, ATE, the NO2 -1. So in this scenario, I can put them together 1 to 1. Okay, so I got 1 sodium and 1 nitrite. Okay, nickel 3. It tells me I'm working with Ni +3, and then the oxide obviously is a -2. And so again, we have 2 dissimilar oxidation numbers. Find a common number means I need 2 nickel 3s and 3 oxides. So our formula would be Ni2O3. Okay. Magnesium iodide, magnesium was a +2, and the iodide is a -1. It's a group 7 element. I need 2 iodides for every magnesium, so it becomes Mgi2. All right, the cyanide, polyatomic ion table, is a -1. We also did that with Lewis dot structures, the cyanide ion. Aluminum all the time, 100% of the time has a +3. Means we need 3 cyanides for every 1 aluminum 3. So we use a parentheses, Al parentheses CN and parentheses subscript 3. Okay. So let me get my mess out and show you the one that's not as messy. All right, sodium nitrite, nickel 3 oxide, magnesium iodide, and aluminum cyanide. And again, you can continue with the mix and the match. Okay. All right. Bear with me for 1 second. I got to do a quick stop. We'll finish this chapter here in a little bit, and then we'll take a break, and then we will continue with the other slides that I want to talk about with far as nomenclature. We'll probably call it a day. All right, so bear with me for 1 second. Okay, I'm back. Sorry about that. My dog was asking to get out, wanted to go outside. The disadvantages of teaching from home. Okay, now with respect to covalent molecular compounds. Okay, we just did ionic compounds, metal, non-metal combination. Thing to remember there, no prefixes. Also, no prefixes for any of them. And then for those that require the Roman numerals, those are the ones that do not belong to the 16 elements that have a constant or an exact oxidation number. Okay. Now, a lot of the naming that we did in ionic compounds follows through for molecular compounds. For example, oxygen. It's oxide, be it covalent compound, be it ionic compound. Okay. Same for chlorine or chlorides and iodides and so forth. All right. So the other aspect is we're not dealing with the ions here. So obviously there's no charges, but there is oxidation numbers. Remember, the term oxidation number encompasses both ionic and covalent compounds, because though there are no full charges on covalent compounds, there are partial charges due to the polarity of the molecule. Okay, so we use the term oxidation number. We do use prefixes, okay? And the prefixes we utilize are mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, and octa for 8. Occasionally, not always, you might see the 9, which is 9 is nana, N-O-N-A, and the 10 is deca. Okay, deca. All right, so we do use prefixes. Now, basically, you're going to be given the central atom, Okay, most 99% of the time it's the first atom first, and it has its name. Yeah. If, for example, the halogens like iodine is a central atom, its name remains as iodine and not iodide. So whatever the central atom and whoever the central atom is, its name is whatever it's given in the periodic table. It is only what's bonded to it that we change it into the IDE if needed. Okay, IDE. So we'll have some examples of that in a bit. Now, if the first metal, if the first non-metal is all by itself, we just give it a name. So for example, we don't use the mono for the first metal. So here we have CO2. So this would be called carbon dioxide. Okay, the di prefix or two. Notice we didn't say monocarbon. Okay, if there's CO, then it'd be carbon monoxide. Monoxide meaning one oxygen, right? Okay. But the first name by itself, no mono. Okay. If it's the second one, yes. If it's one atom, we use the prefix mono. Right. This one here, as I just stated, carbon dioxide. Okay. All right. This one, carbon monoxide. Okay. Now we're going to have numbers here. Okay. So what we do first is, like I did with ionic compounds, we write the parent name first. Okay. It's phosphorus is the central atom. And so we have phosphorus. And then O, I'm getting notation that my internet is unstable. So the parent name is phosphorus oxide. Notice I didn't call it phosphide because in this case, the phosphorus is the central atom. So whatever elemental name it has, it is phosphorus, not phosphide. If it was phosphorus after the central atom, yes, then it would be phosphide. But here it is the central atom. So that's the parent name. And then we go back to see if there's any more than one. So yes, there's two phosphorus, so that becomes diphosphorus. And there are five okay, I lost my connection. We're all back now. You all can hear me okay?
Yeah.
All right. Let me call it back up. All right, so as I was stating, the parent name is phosphorus. And then oxide, that's the parent name. Now we go back to see we have more than one, and yes, we got two phosphorus, so that's diphosphorus. And then we have 5 oxygens, which is penta. Okay, now here's the English part here that if I have penta, I got an A, which is a vowel, and I need to connect it to an O, another vowel, and I'm supposed to drop the A, so that would be pentoxide. Okay, I'm not worried about it. Drop the A or not, that's fine with me. So you can say pentaoxide or you can say pentoxide. Okay, all right. Diphosphorus pentaoxide or pentoxide. Okay, here is phosphorus again. So we got phosphorus and then the fluorine or fluoride Okay, so the parent name, I always, I write the base name first. So we got phosphorus again, and then we got fluoride. Okay, and we go back, we only have one phosphorus, we don't use mono, we just leave it alone. And then we got 3 fluorides, so it's trifluoride. So we got phosphorus trifluoride. Okay, now notice here iodine is the central atom. Okay, and so its name is iodine. If it was not the central atom, then it would be iodide, but the central atom is written first. And then we have fluoride. Base name, iodine fluoride. There's only one iodine, so it remains as iodine. And then there are 7 fluorides, so there's heptafluoride. Okay, so 7 fluorides. So we got iodine, heptafluoride. Excuse me. Okay, given the formula, write the name and vice versa. So for example, here, bromine is written first. That is the central atom, okay? I know we're used to having bromide because it's bonded to something else, but here bromine is the central atom. And so the parent name is bromine. And then oxygen, which remains as oxide. Okay. Then we go look for the numbers. There's 3 bromines, so it's tri, and then 8, and that's octa, drop the A, or not drop the A, so octoxide or octaoxide, either one will work. Here we have phosphorus and sulfide. So we got phosphorus, and sulfide. Notice that sulfur is not the central atom. It comes after the central atom. Okay, so the name goes to sulfide. Unlike if it was written SO2, then that would be sulfur. Okay, because it's the central atom, then dioxide. Note the difference, right? Okay, sulfur when it's the central atom, sulfide when it's not the central atom. So here we got phosphorus sulfide. We got tetra for 4 phosphorus and hepta for 7 sulfides. So we go tetra, phosphorus, heptasulfide. Here we go, sulfur. Again, sulfur was not the central atom. And then oxygen, which is oxide. And there's 3 of them. So we got sulfur trioxide. Okay, it was 2 sulfur dioxide. Okay, notice, don't confuse this sulfur dioxide, trioxide with the polyatomic ion, sulfite. Okay, note the difference. They both have sulfur and 3 oxygens, but the difference is this is the polyatomic ion with a -3 charge. The SO3, sulfur trioxide, is a neutral covalent compound. Okay, now you're being asked to do the opposite. You're given the name, give me the formula. So just reverse it. Write the parent formula first. We're dealing with iodine and we're dealing with fluoride. Okay, and so we got iodine and fluoride. So that's the parent, like I did earlier, where I did the parent name, then I come in with the prefixes, I reverse it, I write the parent structure name, the formula, then I go back and do the numbers. So there's only one iodine, and there are 6 fluorides. So that formula becomes IF subscript 3. Okay. All right, here we have chlorine and oxide. Notice it's not chlorides. Chlorine is the central atom. Cl and then O for oxide. All right, di, so it means we got 2 chlorines and 5 oxides. So chlorine pentaoxide. All right, and then here we have the name, the formula. We want to figure out the name. And so we do the same thing. Parent name, so we got phosphorus. And then I for iodide. Okay, then we come back 2 phosphorus, so it's di, and tetraiodide, tetra. Okay, tetraiodide. Let me clear this up and do the clearer picture. Okay. Diphosphorus tetraiodide. Okay, reminders, only prefixes for covalent compounds. Okay. And Roman numerals only for variable charges. And polyatomic ions, we don't change their name. It is what it is, their name. And then those are the main reminders. So, all right, write the formula and the name. You got top one, we got barium chloride, okay, nitrogen dioxide, iron 2 phosphate. There you go. So try those and see what if you got any question about them, we can go over them. What I want to do now is take a quick, take a 15-minute break. And then I want to go over the files that I've uploaded for you concerning nomenclature, concerning specifically the naming of polyatomic ions. Those are things like the nitrate and the nitrite. There's a systematic approach to giving their names and so forth. So this will help you with respect to the nomenclature exam. Okay, and so let's yeah. Don't forget we got a worksheet here. You might want to work that. All right, so that's the end of chapter 8. And okay, I'm back. What I want to do is share with you a couple files that I have uploaded concerning nomenclature of variety of things. Okay, let's try. Let me upload this one first. Okay, there is a file uploaded. It should be in the module labeled nomenclature, but what this is a listing that by all means not a complete list of common polyatomic ions, okay, besides the ones that I gave you on the periodic table. And you can see all of it with the -1 charge, -1, bromate, bromite, so on and so forth, okay? So there's that file. And there's some metals, monatomic ions. You can see the different oxidation states they may have. Like manganese could be a +4, it could be a +3, etc. And that's why we need Roman numerals to distinguish them. Okay. Now the other is a nomenclature for common acids. Now, we got binary acids, like for example, hydrofluoric acid or hydrochloric, common binary. Binary meaning there are just two elements, a hydrogen and the respective anion. So HCl, the hydrochloric acid we find in our stomach, is given there. You got all the halogens actually, hydrofluoric, hydrochloric, hydrobromic, hydroionic, even the cyanide, CN ion that we did, polyatomic ion, we put the hydrogen back on and you have hydrocyanic acid. Even the sulfide. See, all these anions, like the sulfide, the -2, if we put a hydrogen back on that charge, hydrogen has a +1 charge, and we can recombine it. So the cyanide, let me do it this way. And so we have the cyanide ion with a -1 charge, and we have what we call a proton, a hydrogen with a +1 charge. If we put them back together, you generate the HCN, the hydrocyanic acid. If you have the same plus hydrogen ion, okay, and let's say you got the chloride, you put them back together and you generate hydrochloric acid, okay? And so on and so forth. These are the binary, just two elements. Now, when we're dealing with oxyacids, we first have to deal with the corresponding salt, like for example, the sulfate polyatomic ion, okay? If we put two hydrogens back on, H pluses back on, we actually create the acid again, H2SO4, now it's neutral, and that makes it sulfuric acid. So all of these polyatomic ions actually came from these acids, and these acids were reacted with the base. We're going to have a whole chapter on that, where you get an acid and the base react, and you form the corresponding salt. And so we're going to talk about the SO4, the SO3, the CO3 carbonate, and so forth. Okay, here's the phosphate, PO4, polyatomic ion. And if we put 3 H pluses back together and regenerate phosphoric acid, H3PO4, okay? And there's some other ones in there. There's a listing of them and some common names. All right, now let me clear my mess up here. So what I'm going to do is talk about these, what are called oxo acids, actually the oxo polyatomic ions, okay? And then from there, if we put the hydrogen back on, we can create these oxo acids back together again. All right, so let me start to share here and go back to the table. Okay, now, if you look at the periodic table, you'll see we look at the periodic table and starting with boron and carbon and nitrogen, okay? And then we don't work with oxygen or fluoride because they're not involved with these oxy ions, except oxygen is obviously, but not by themselves. So here's boron, carbon, and nitrogen. So this is a group 4A, group 3A, which is boron, and then group 1 second here, going to change color. So this is group 3A, and then 4A, 5A, okay, 6A, and then 7A. Okay, so in looking at the periodic table, we're dealing with boron, carbon, and nitrogen, not oxygen or fluoride. Okay, and then we go down to silicon and germanium and stannous, all in the same periodic table. Then under nitrogen, we go down to its respective up to SB right here. Okay, and then starting with sulfur down to TE, and then the chloride, iodine, bromide, and iodine. Okay, so only that part of the periodic table. So let's clear it up. Now, above boron, we put the charge -3, and I'll explain that first in a second here, okay? And then under group 4A, we put the charge in -2, and then next group over -1, okay? Now underneath, all the yellow, starting with silicon down to 10, we got a -4. Then the next group over, -3, and -2, and then finally -1. These are going to be the corresponding charges of the parent polyatomic oxy ion here, okay? Now, starting with boron, this is the parent name. This would be, all of these would have the ATE extension, suffix, ATE. We'll get to the naming here in a bit. From the parent name, then we're able to either remove oxygens or add oxygens to give us the ITE and some other names, okay? So we start off with boron, which its parent